So let's talk a little bit about hyperbolic PDEs first. So first of all, in physics or engineering, hyperbolic PDEs usually arise out of wave-like phenomena. Okay. Classic examples would be partial differential equations which describe vibrations of objects like strings, membranes, beams, any kind of structural component. Okay, so it's used a lot in solid mechanics. Also, if you look at the Maxwell's equations, which are equations of electromagnetic wave propagation, they are also wave equations or hyperbolic wave equations. They have exactly the same structure as the wave equation that we are going to talk about. Of course, the Maxwell's equations are vector equations, just like the Navier-Stokes equations for fluid flow are vector equations. So they have, there is one equation for the electric field, one equation for the magnetic field, and each equation has three components. So you end up with 6 partial differential equations. But the form of each one of them is like the scalar hyperbolic wave equation that we are going to talk about. Okay. Another common example is the inviscid fluid flow or Euler equation. If you go back to your lecture notes, lecture number 1, where we classified partial differential equations, that's one of the examples I showed you, the Euler equation, and we found out that when we classified it and applied it or compared the equation to the standard partial differential equation form, it turned out to be hyperbolic. Okay. The Navier-Stokes equations for fluid flow, which many of you may be using down the road or are already using, that's a very unique equation because it has actually all 3 characteristics. Okay. Now, one thing you have to realize is when we classify partial differential equations, if you go back to lecture 1, we have this equation which says A d square phi dx square plus B d square phi dx dy plus C d square phi dy square plus other terms equal to some terms. Okay, but these are the 3 main terms. You can see here clearly that this classification is based on the fact that we have only 2 independent variables, x and y. Okay. So one of the issues that always comes about when you classify partial differential equations is what happens if I have more than 2 independent variables. So suppose now I add a time derivative to this equation. Okay. Then how would you, which of the 2 independent variables would you look at to classify the partial differential equation? Okay. And in that case, what happens is the definition becomes quite ambiguous, or the classification, and you have to actually assign sort of qualifiers to whatever your statement is. For example, if you look at the equation d phi dt is equal to alpha d square phi dx square plus alpha d square phi dy square, this is the parabolic heat conduction equation that we've been talking about. This equation is actually elliptic in space because of this operator here. Okay, but if you now strike out that guy, the rest of this equation is actually parabolic in time. Okay, it's a parabolic equation. So when people classify these kinds of equations, they add these qualifiers saying it's elliptic in space and parabolic in time. Okay, rather than saying it's an elliptic equation or a parabolic equation, because it has both characteristics. Okay, depending on which of the independent variables you use to classify it. If you use x and y, then it's elliptic. If you use just time and x or time and y, then it's parabolic. Okay. So from that perspective, if you look at the Navier-Stokes equations, it has all 3 characteristics. It's actually elliptic in space, and then the time dependence could be either parabolic or hyperbolic depending on what your Mach number is. Okay? If you're in the subsonic flow regime, then it's a parabolic equation in time. If you're in the supersonic flow regime, it's hyperbolic in time. Okay? So there are all these issues that you get into when you look at actual equations derived or that are used in physics or engineering. Okay, but here, of course, in this class we are looking at only canonical partial differential equations. So we are pretty much sticking to partial differential equations that are of one type. Okay, but I want you to keep in mind that not all equations can be just purely classified into one type. Some of them are mixed. They have mixed characteristics. Okay. Any questions on that? All right. So just move on here and talk about the hyperbolic wave equation. So the Euler equation is actually just one half of the Navier-Stokes equation, where you throw away the viscous terms, and that's why it becomes purely hyperbolic. Okay, if you include the viscous terms, then it also becomes elliptic partially. So that's part of the problem. Okay, so generally a hyperbolic partial differential equation is written as that. This is what's called the classical wave equation. Okay, where phi is your dependent variable. Okay. And then the c square, c is the speed of propagation of the wave. Okay. And of course I can also add d square phi dy square for multidimensional, spatially multidimensional version of this equation. Okay, but let's just stick to just x so that we have only two independent variables and we can clearly say that this is a parabolic equation or a hyperbolic equation. Okay. Now if you go back to your comparison, so this is what I was just showing you. This is your standard form of a partial differential equation in two variables. Okay, if you compare this hyperbolic equation to that, you clearly see that a is equal to 1 because the coefficient in front here is 1, and then if you pull this term over to the other side, this becomes minus that is equal to 0. So therefore b is equal to 0, of course, because we don't have cross derivatives, and then c becomes equal to, actually this is not minus 1 but minus c squared. Okay, so therefore your b square minus 4ac becomes 4 c square, and c square of course is always a positive number because it's square of something. Okay, and therefore b square minus 4ac is greater than 0, which makes it a hyperbolic equation. All right. Now in the first half of the semester we looked at, or we worked quite a bit with the Poisson equation. You just turned in a homework which solved the Poisson equation. Okay, that's of this form. Now notice that if I look at this equation versus that equation, both of them are second order linear ordinary differential equations with two variables. Both of them have second derivatives in both variables. The only difference is here I have a minus sign. Okay, if let's say you set c square equal to 1. Okay, the only difference is here you have a minus sign, here you have a plus sign. Okay, and just by doing that, of course, this becomes hyperbolic and this becomes elliptic. If you do the same comparison, here you will find that b square minus 4ac is minus 4, which makes it elliptic. Okay, so just by changing one sign, you've changed the type of partial differential equation it is. Okay, now why is that important? Well, it is important, or why do we need to differentiate between these two types of equations? Why can't we just say, okay, it's a second order ordinary differential equation with second derivatives in both independent variables, and therefore we are all set. Okay, we can apply the same numerical techniques to both equations. The problem is that it's not really, it doesn't have to do with the numerical technique per se, but it has more to do with how you pose the problem. Okay. The theory of partial differential equation says, so this is what I just mentioned, that both of them have second order PDEs in two independent variables. Okay, but the theory says that now, of course, since it has second order, since it's a second order PDE in two independent variables, you will need at least two boundary conditions in each of the two independent variables. Obviously, if you have a first order differential equation, you need one boundary condition. If you have second order, you need two boundary conditions, and so forth. Okay, that we know. But the big difference between The elliptic type and the hyperbolic type is where you apply those boundary conditions. Okay. In elliptic boundary conditions, if you go back to the theory of differential equations, it states that if you have an elliptic partial differential equation, you must specify boundary conditions on all bounding surfaces of your domain. Okay, so if I am analyzing an object which is of this shape, I must specify boundary conditions on all these surfaces. Can't leave out even a single point. Okay. If you do, then that problem is ill-posed. You can't solve it. Okay, if it's an elliptic partial differential equation. So if I look at, let's say, a rectangle like that, I'm saying I need one boundary condition here, one here, one here, one here, which is what you're doing for your homework. Okay, I need 4 boundary conditions. 2 in the x direction, 2 in the y direction. All right. When you get to hyperbolic PDEs, it's quite different. Okay. For one of the independent variables, both conditions must be specified at the same boundary. Okay, not on 2 different boundaries. So if I'm looking at, if I draw a picture, let me just clear up some of the space here so that I can go back to my picture. So suppose instead of x, y, I say, let me just wipe this. Instead of x, y, I say, okay, I have time in this direction and x in that direction, because my equation is d square phi dt square minus c square d square phi dx square equal to 0. Okay, so therefore I'm instead of x and y, I'm using x and time. Okay, so I'm saying, okay, time is in that direction, x is in that direction. Hyperbolic PDEs, if this was a elliptic PDE, I would say, okay, I need one boundary condition here for x, another one here for x, one here in time, or sorry, the other way around, one here in x, one here in x, one here in time, one here in time. Okay, but for hyperbolic PDE, you will need boundary conditions in x here and here, and 2 boundary conditions here in time, at time t equal to 0. Okay. No boundary condition at this edge at all. Okay. Why? Because the physics of hyperbolic equations is such that downstream information never affects upstream information. In other words, what is happening in future time does not affect what's happening before. That's the physical explanation. Okay. What's going to happen 100 years later is not affecting what's happening now. It's the other way around. Okay. And other way around, you need 2 conditions. You need 2 conditions at time t equal to 0, because obviously it's a second order differential equation, so you must have 2 boundary conditions. There's no way around that. Okay, but they both have to be specified at the same location. Okay, that's the main difference when you get to classification of partial differential equations. The boundary conditions, that becomes the key issue. How and where do you specify the boundary conditions to make the problem well posed? Okay, any questions on that? Okay, so I was talking about supersonic flow. The same idea, when the flow becomes supersonic, downstream information doesn't affect upstream information at all, because the pressure waves cannot travel back in time. So that's the same idea there. Okay, so let's move on, and so that's our governing equation. Okay, so our domain here, if I'm looking at sort of a rectangular regular domain, okay, then x is between 0 and L. Okay, and t is starting at time t equal to 0 and going up to infinity. So it's the second variable in this case we are looking at, it's semi-infinite. Okay, and as I said, c here is the speed of propagation of the wave. Okay, so boundary conditions, we can say at one end x equal to 0 we have phi left, and x equal to L we have phi right. okay, just like you've been using for your elliptic problem. Same idea, okay? And then we get to initial conditions. We call them initial conditions. Sometimes mathematicians call them boundary conditions in time, okay, because they don't distinguish between time and space. They just think of it as independent variables. But typically in an engineering class, we would call them initial conditions because they are conditions in time. So you need two boundary conditions, okay? Typically, you would need a Dirichlet boundary condition to anchor the solution, and then you will need one other type. It could be a Neumann type, or it could also be a mixed type, okay? Now, this is the most general type of boundary condition that you will find, where the variable itself is specified at the boundary, Dirichlet condition, and the derivative with respect to time is also specified at the boundary. And these two in combination is also known as a Cauchy initial condition, okay? Now sometimes in some problems, instead of this second boundary condition here of the Neumann type, you might encounter a mixed type like that, which is the Robin boundary condition, okay? So you will have one Dirichlet condition and you will have one of these conditions, okay, which is a mixture of Dirichlet and Neumann, the Robin boundary condition, all right? That can happen in some problems, but in most cases you will encounter something like this. Okay? Any questions? All right. So now we want to, of course, solve that equation, the partial differential equation. So we are going to start with our Taylor series expansions in time. So our objective is really to discretize this guy. Okay? This guy we already know how to discretize. That's your standard central difference. All right. We are looking at discretizing the second derivative in time. When we did parabolic equations, we discretized the first derivative in time. Now we have to do the second derivative in time. Okay. So we do two Taylor series expansions, one forward, one backward in time. So I'm doing n plus 1 about n, and then n minus 1 about n. This is kind of like the same idea as central difference in space, okay? Central difference in time, essentially. So if we add the two expressions, then we get the second derivative in time, which is exactly the same kind of expression as we have as central difference in space. And you can see even the error expression is identical, except instead of dx, you have dt. All right? So nothing different there. It's second order in time, as you can see, the error. Okay. So we plug that into our governing equation. And of course, we want to satisfy that if I now use an explicit method, which is what I'm looking at here, the right-hand side, I must have everything at n. Okay. I'm trying to solve for n plus 1. All right. So same idea as a parabolic problem. The right-hand side, we are setting it at n. And therefore, we can rearrange that formula to give us, or that equation to give us this formula. You see what this requires now is to calculate this guy, n plus 1. I need not only n, I also need n minus 1. Two time levels. Okay? Because it's a second derivative in time, so it makes sense that we're going to need two time levels, which obviously implies that, so this is a pictorial representation. You're trying to find this value, okay, and you need all these guys and also this guy. Okay. Now, obviously, that means that when I'm going from 0 to 1, I can't use that formula because I don't have a I don't have a minus 1 here. Okay. In other words, I don't have this time plane. I'm starting from n equal to 0. So when I'm going from n equal to 0 to n equal to 1, I can't use that equation. It's very similar to saying that, okay, when I'm getting close to the boundaries, I can't use the same interior node equations that I used in space. Okay, I have to derive special equations for the boundary nodes. Okay, same idea, but in time. All right. So the next thing we are going to do is, so we are going to remember that, okay, this is for n greater than 1 only we can use it. Okay, from n equal to 2 onwards. And now we have to derive an equation for this time plane, n equal to 1. All right. Okay, so how do we do that? So again, we start with a Taylor series expansion, a forward Taylor series expansion, as you can see, n plus 1 about n. Okay, and now what we are going to do is we are going to substitute in both initial conditions. This is kind of like what we did for spatial derivatives and boundary conditions. Okay, same idea. Instead of phi I at n, we are going to plug in our alpha I. Alpha I is nothing but, let me just go back here to the problem definition. Here, this is your alpha. Okay, so phi at time t equal to 0 is alpha, and the derivative at time t equal to 0 is beta. Okay, so that's what we are using here. Plugging in alpha I here, and then instead of the derivative, we are plugging in beta I. All right. So once we do that, then we can rearrange it to get our second derivative. And it turns out that the second derivative is only first order accurate. Okay. Now, again, we do expect, because this is, we are using just two Taylor series expansions. Remember when we did central differencing in space, okay? We got second order accuracy, but that was fortuitous because the third derivative canceled out because we used equal delta x on both sides, okay? If we did not use equal delta x on both sides, we wouldn't get the third derivative to cancel out. We would get actually first order accuracy. Okay, or somewhere between first and second order. Same thing is happening here. In the previous formula that I showed you, this guy here, this one has second order in time, but that's just fortuitous because we use the same delta t, in going from one time step to another. If you don't use the same delta t, then you are not going to get second order accuracy with that. Okay. Now, at the boundary, when we use the Taylor series expansions, we end up with first order accuracy. Okay, and that's because, we are making use of only one Taylor series expansion in this case. Okay, you could make use of another Taylor series expansion also, where you go phi I at n plus 2, okay, about phi n, and then try to derive a higher order approximation of that. But generally, people don't do that. Okay, so because this is kind of like the forward Euler method for the parabolic counterpart. Okay. Any questions on that? So, and I'm making a note here that the first order accurate in time scheme is not too bad in this case because it will be used only in one time step. From the second time step onwards, you are back to second order, okay, which is the other equation that I showed you. So you substitute that back into your governing equation, and again you rearrange and you get your explicit integration formula. And notice that this is now what's going on. To calculate that value, you need these three values. Okay, so this is only the first time step, and then previous slides I already showed you what happens from n greater than 1. Okay. Any questions? So that's your explicit method. All right. Here's the algorithm. You set up initial conditions for all nodes. So this is your n equal to 0, time t equal to 0. Remember, t time is equal to n delta t. Okay. So therefore, when n is equal to 0, time is equal to 0. You're starting with your initial condition, and then you calculate all nodal values at the first time step. So first time step, we are using this special formula which uses the initial conditions. Okay. Then once you're done with that, you reset your initial condition. So once you've solved for the first time step, that becomes your new initial condition, and you're ready to move on to the second time step. Okay. And for that, of course, we have a different formula than the first time step. And again, you reset your initial condition, and you repeat steps 4 and 5, which is these two guys, for subsequent time steps. Okay. Any questions on that? So it's pretty straightforward in terms of implementation. Okay, and once you're done with your parabolic homework, you'll find that you can just take that exact template and just replace the equations by these equations. That's all. All right. Okay, so now comes the question of stability. Of course, we know explicit methods are known for instability, as we've seen in the parabolic partial differential equation case, which had that stability criteria of what was it, alpha delta t over delta x square must be less than or equal to half. Okay, here we need to look at, okay, is this method stable or unstable, and if there is an instability associated with it, is there a stability criterion? All right. So we start with our governing. Now, of course, what I'm doing here is I'm skipping the first time step. So the first time step, I'm assuming, okay, let's forget about the instability of the first time step. We'll just look at n greater than equal to 0. It's kind of like doing stability analysis in space where, you know, we never looked at boundary nodes. We always looked at the interior nodes. All right. Because this is the generic equation that's valid across all other time steps. So we're starting with that and following the same procedure as we've always done. If you go back to the stability analysis of parabolic equations, we are following the same steps. We have an error equation now. Okay, so basically that translates to the error equation. And then this is your modal expansion, Fourier mode expansion, where the stability criterion is this complex amplitude xi must be between -1 and +1, or its magnitude must be less than 1. Okay. So this is exact same thing as what we did for parabolic equations. So now what we'll do is, first of all, we will shift the origin to node j as we did before. So make our central node 0, and then I plus 1 will become just +1, and I minus 1 will just become -1. Okay, that's what we are using here. And then we are also getting rid of the summation sign, because we know that the Fourier modes are independent, so each mode must satisfy this equation. Okay, so we've gotten rid of the summation sign. So if you plug into this equation, you can see that this guy will give you xi. This guy will give you basically exponential of 0, so you will be left with the -2, and then this guy will give you a minus xi, okay, which will give you, or xi to the power -1, and then here you will have an exponential of plus I theta, minus I theta, and then here, of course, you'll get exponential of 0 again, all right, which will give you this -2. So this is following exactly the same procedure as we did for parabolic equations. Again, if you are confused, I know I'm kind of skipping a few steps here, not going through nitty-gritty details, but if you're confused about that, just go back to your notes for the parabolic equation, okay, where it's explained in more details. So we get this expression, we simplify it, we get that, and then we use this relationship that we have always been using, which is cosine theta minus 1 is equal to 2 sine squared theta over 2. Okay. So using that, and the reason we do that, as I explained all the time, is because we cannot judge what the sign of cosine theta would be, because it could be positive or negative, but we can judge what the sign of sine square would be, because we know it's always positive. Okay. So that becomes your equation. Now, of course, one of the problems you see is if you rearrange it further, you see that this is a quadratic equation in xi. Okay, somewhat more complex than what you get for parabolic problems. All right. So if you solve it now, before I solve it, I'm using a shorthand notation where I'm calling g as this big term within brackets. Okay, this is my g. So I get, and also I'm using the symbol r, which is this guy, c delta t over delta x, that ratio. So therefore, this g is 2 minus 4r squared sine squared theta over 2. Okay, so just introduce two new symbols, r and g, just to simplify the math. Okay, Now this r, by the way, has a special name. This is a non-dimensional number. You can see this c has units of meters per second because it's speed, right? Delta t is in seconds and delta x is in meters. So the units cancel out, you get a non-dimensional number. C delta t over delta x is a non-dimensional number. It is actually called the Courant number or CFL number. Okay? For those of you who are doing high-speed gas dynamics calculations, you're probably familiar with this. This was first proposed by a pioneering paper by these three guys, Courant, Friedrich, and Levy, in 1928. They were, in fact, the founders of the finite difference method. Okay? They first introduced, in the same paper, they introduced the finite difference method for parabolic problems, and then they also did hyperbolic problems, and they looked at the stability of hyperbolic equations with explicit time marching, and they came up with this criterion that we are going to talk about shortly. Okay, so this is called the CFL number. Okay, physically, if you look at this, there's a physical meaning to this number. Okay, if you look at C delta t, what is that? That is how much distance the wave propagates in time delta t. Right? Because c is the speed of the wave, delta t is the time step. So it's telling you, okay, the speed, the wave is moving from here to here in time delta t. Okay? In the denominator, you have the grid spacing, delta x. So you're comparing how much the wave moves in one time step to what is your grid spacing. Okay? That's what you're comparing. Now, later on, we will see that, of course, whatever stability criteria we get, you will see that it kind of makes sense from a physical perspective. If we now think about that physical picture of how much the wave is moving in one time step versus the grid spacing. Okay? Any questions? All right, so getting back to our equation. So we have this quadratic equation. If we solve it, we get these two roots. Okay? So I'm just using the formula b square minus 4 or minus b plus minus b square minus 4ac over 2a. Okay? So those are your two roots. First observation to make is that when sine squared theta equal to 0, that is if I make this guy 0, okay, then g becomes equal to just 2. You can see g becomes 2. Okay? And then both roots in that case become equal to 1. Okay, so that means when sine squared theta over 2 is equal to 0, this is not a relevant case because it doesn't give us any kind of stability criteria. It simply says that you are within the stability bounds. Okay, because the stability bounds say that xi must be less than or equal to, or magnitude of xi must be less than or equal to 1. Okay, in this case we are getting exactly 1 with sine squared theta over 2. So let's look at the other extreme, which is sine squared theta over 2 equal to 1. Okay? And we start with the first root. So first root is this one, xi 1. Okay, this was our xi 1. And the criteria for stability, remember, is that xi must be greater than or equal to minus 1, must be less than or equal to plus 1. This is our criterion for stability. So we are starting with this lower limit first, applying that to xi 1. Okay? And if we do some math, of course, we can rearrange that and then square it. And once you do all that, you get 4g is less than or equal to minus 8, which gives g is less than or equal to minus 2. Okay? Now, our g is 2 minus 4r squared sine squared theta. Of course, sine squared theta we are using equal to 1. Okay, so therefore we get 2 minus 4r squared. So what this inequality gives us is 2 minus 4r squared is less than minus 2. Okay, you rearrange that further and you end up getting r squared is greater than or equal to 1. So what that's telling us is c delta t over delta x squared is greater than or equal to 1. Okay. Now, if you really think about it, it's basically saying that if you use large time steps, then the above criteria would be satisfied, okay, which is kind of very odd. it would almost suggest that if you use small time steps, things would blow up. Okay, so then the question becomes is, okay, fine, I don't mind using large time steps if you're saying that's stable. Okay, but does it mean that small time steps are unstable? What happens there? Okay, so suppose I use small time steps. In other words, I don't use r square is greater than 1, but I use r square between 0 and 1, less than 1, r square less than 1. Of course, it has to be greater than 0, okay, because it's a square of a number. Then I get this guy, g is less than or equal to 2 and greater than or equal to minus 2. And that leads to complex roots. So if you use g in that range, you will find that this root is complex. Okay? And so if you now compute the magnitude of that root, you will find that the magnitude is always unity or 1, no matter what the value of g. Okay? Here's a little example. So suppose I use r equal to 0.5. All right, so this is the CFL number equal to 0.5. Then r square is 0.25, g is equal to 1, and therefore xi1 becomes 1 plus square root of 3i over 2. Okay, I being the complex number, the imaginary number, sorry, square root of minus 1. Okay, so therefore your xi1, magnitude of xi1 becomes exactly 1. Okay, and you can try it for any number. You'll find that it's always 1. All right. So this implies that smaller time steps will also be stable. So basically, using xi1 and the lower limit, we haven't come up with any stability criteria. We are basically saying small and large time steps will be stable. All right. Really nothing meaningful, at least when we look at xi1. Okay. So lower limit is satisfied with any time step. That's our conclusion. What about the upper limit? Upper limit gives us this inequality. Okay. And again, we do some algebra on it. That gives us g is less than or equal to 2, which means 2 minus 4r square. Of course, sine squared theta is equal to 1. So 2 minus 4r square is less than 2, which gives us 4r square is greater than 0, or r square is greater than 0. And that's pretty obvious. Again, that doesn't give us anything new. Okay, r square obviously will be greater than 0. It's a square of a number. Okay, so again, nothing new when we look at the upper limit. So basically what we are saying is that when we analyze the first root that we get out of the stability criterion, we do not get any meaningful information in terms of what our delta t should be, okay, if at all anything. It's basically saying, you know, nothing useful. So we move on to now the second root. Second root is this guy. So instead of a plus sign here, we have now a minus sign. Okay. So the first root had a plus sign there, now we have a minus sign. Same kind of analysis. We are starting with the lower limit. We do some algebra. We get g is greater than or equal to minus 2. Okay. Now again, this is equal to 1. So therefore 2 minus 4r square is greater than or equal to minus 2. Or r square is 4r square is greater than 4, or r square is less than 1. Okay. This guy is less than 1. That's a valid stability criterion now. Okay. So this criterion for stability of an explicit method for hyperbolic PDEs is that the CFL number must be less than 1. Okay. This is what you will find in you know, CFD books and so forth. Typically, you may not find a derivation, but they will mention it that you got to use CFL numbers less than 1. Okay. Now, if you use the upper limit, so going to, you know, this less than plus 1, then what you will find is that it will give you basically this criterion: r square is less than 0, which again doesn't have any physical significance because that's only possible with complex r. Okay, it's not possible with real r, and r, of course, for our particular case has to be real. Okay, so we are just going to ignore that because it doesn't give us anything meaningful. The only meaningful criterion we get is this one, or summarized here, that is the CFL number must be less than 1. Now, getting back to what I was talking about earlier about the physical interpretation of the CFL number, that C delta t is the distance traversed by the wave. Okay, delta x is the grid spacing. So basically this is saying that if you take a time step where the wave moves more than one cell, you will hit an instability right there. You can't move more than one cell in one time step. That's all this is telling you. Okay? Your time steps have to be small enough that the wave propagates no more than one cell within that time step. All right? Any questions? So our criterion for stability, so this is just a summary of what we found. Okay? So I'm plotting R, which is our CFL number, okay, versus xi on this axis. So basically what we are finding is that when R is less than 1, then both xi1 and xi2 are complex with magnitudes of less than or equal to 1. Okay, and out of the two roots xi1 and xi2, one of them is, as you can see, this guy here is the stable guy. It has actually a value between 0 and 1. Okay, and this guy, the xi2, is the unstable one when you get to r greater than 1. Okay, that's just a summary of the results that we found. So the stability criterion is best illustrated, I'm saying here, using a simple example. So I just want to give you a simple example. I'll show you a numerical example in a bit, but this is just a simple back of the envelope type of calculation. Okay, so we are going to solve this governing equation, one dimensional, and we are going to apply it to the displacement of a string. Okay, so the string is anchored at the two ends. You can see 0 and 1 both have displacement of 0. So it kind of looks like that. Okay, at both ends it's anchored, and then what you do is you initially pull it up to some displacement and then you release it. Okay, so it's like a rubber band anchored at two ends. You pull it up and then you let it go. Okay, now physically the amplitude that you get here, it cannot exceed, if this amplitude is 1 and this is -1, it cannot cannot exceed those bounds. Okay, it's not possible. It would violate energy conservation essentially. All right. So so now the question is, okay, if we do explicit time marching, what happens really? Okay. So now what I'm doing here is I'm imagining that I'm doing a finite difference solution where this guy is discretized using just 3 nodes as I've drawn. So 1 interior node and 2 boundary nodes. Okay. The 2 boundary node solutions I already have. The interior node is the only unknown, and I'm trying to solve for that. Okay, so I'm starting with time t equal to 0, and I want to solve it for time t equal to delta t. Right? So I already mentioned this, that the solution must be bounded by +1 and -1. And to set up the explicit solution at the second time step, we need the solution of the middle node at both n equal to 0 and n equal to 1. And let us assume that these solutions are both 1. Okay, so in other words, the string was displaced and held for some time. So at n equal to 0, it was like that. N equal to 1, it was also like that, and then you let it go. Okay. So if we now plug in those conditions here, you basically get something like this. So phi2, so 2 being, my nodes are numbered like this: 1, 2, 3. Okay, so this is phi2 at time step 1. Okay, that is equal to 1 as described here. phi2 at time step equal to 0, that's also equal to 1, and then I have this r square showing up in my equation, okay, the CFL square, and then phi3 at 1 is 0, because that's the boundary condition. Phi1 at 1 is 0, which is also the boundary condition, so these two are just 0, and then we have 2 times 1, which is our initial condition, this guy. Okay, so that gives me 1 minus 2r square, and you can immediately see that if I put in any value of r greater than 1, I immediately exceed those bounds. Okay, so as long as r square is less than 1, the solution is between plus 1 and minus 1. The moment you exceed r square greater than 1, your solution becomes unbounded. Okay. So basically what happens is you take a large time step, this string is starting to move, you're not correcting for its change in speed or change its displacement and speed as it's propagating. So it just takes that initial value and boom, it overshoots the location at the bottom, okay, and you get an unbounded solution. Okay. Any questions? I'll show you a numerical example. Let me just get out of this before we do implicit methods. Let me show you a numerical example. So here is the actual numerical example. Let me make this bigger so you can see it. So we're solving this. I've chosen c square equal to 1 in this case. And then what I have is an initial condition which looks like this. So basically that's like a string, which has been pulled up like that and then like that. Okay, so this profile that you see here, 2x and 2 minus 2x between x equal to 0 and 0.5 and 0.5 and 1, that's this profile. Okay, it's a piecewise linear profile. That's my initial condition. Okay, and then initial velocity I'm setting to 0. All right, or I shouldn't call it velocity, but d phi dt. Okay, so the analytical solution. Now these types of partial differential equations, there are two ways of solving them analytically. One is to do separation of variables, which many of you are familiar with, right? Anybody who's taken partial differential equation classes? Yeah, so you must be familiar with separation of variables. So you can use separation of variables for this solution. The other way of solving this is what's called the D'Alembert solution. Okay, so there's this special transformation that you can do if you define a new variable, let's say x star, okay, as x minus ct and or x plus ct. Okay, you can basically superimpose two solutions and find that solution. That's how the D'Alembert's principle works. You can derive this analytical solution. Okay, so the analytical solution, you can see there's a cosine function in t and a sine function in x. Okay, and this is of course an infinite series. So what I'll show you here are solutions with CFL number equal to 0.5. Okay, so that's within the stability bounds. Okay, so these two plots here. So this is actually showing you the solution. The red, blue, and green lines are at different instances of time, and it may not be very evident from the back there, but there is a solid line which is showing the analytical solution, and there is a wiggly dotted line which is showing the explicit numerical solution. Okay, now it may, as I said, it may not be evident from the back, but it actually depicts slight oscillations around that flat line. Okay, now these flat lines, by the way, are very difficult to exactly replicate numerically. You know, for example, if I asked you to fit a line like that with a polynomial, that's one of the hardest things to do. Okay, if I say, okay, fit a fifth order polynomial to this line, you are going to get these wiggles around that line. Okay, there's no way to avoid it. So you see with the explicit method also there are these tiny wiggles, and if I look at the errors between the analytical and numerical solution, then you basically end up getting these kinds of very noisy profiles. They're of course nice and symmetric, they're not noise, but you see these kinds of error profiles. The actual magnitudes are pretty small compared to 1, okay, but they are there. All right, but the solution is stable. If you go to higher time steps, what happens is this whole thing keeps going down, 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 and then you get the same kind of patterns in the negative direction. All right. All right, now I'll skip forward and show you what happens when you use higher CFL numbers. Okay, this is what happens when you use CFL of 2. Okay, the left figure here. Forget about the right figure. The right figure we'll get back to later. But you can see here 0.05 seconds and 1 second, 2 solutions are shown. The solution around the red line, you see that wiggle, big wiggle there, but it's still stable. But by the time you get to slightly larger time steps or slightly larger instances of time, the solution has just blown up. You get these huge oscillations, and ultimately it'll just start giving you nans on your computer. Okay, so very similar to what you saw for the parabolic problems, where if you violate the stability criterion, maybe for some period of time it's still going to stay stable, but eventually it will blow up. Okay, any questions on that? All right, let's get back to our lecture here. So that brings us to the implicit method, because that's the natural flow. We know explicit is unstable, so how can we improve it? We do implicit. Okay, same idea. We are starting now with Taylor series expansions, but now because this is an implicit method or a backward Euler method, we can do only backward Taylor series expansions, which is what we are doing here. Okay, we are going back in time, so expanding about the present being n+1. Okay, here we are going, as you can see, 1 time step back in time, and here we are going 2 time steps back in time. Okay, and we multiply first equation by 2 and subtract the second equation. Why do we do that? Well, because we are trying to derive a second derivative. We want to cancel out the first derivative. That's our objective. So therefore, to cancel out the first derivative, we must multiply this equation by 2. Otherwise, these two will not cancel out. Okay, so that's why we multiply first equation by 2 and subtract from the second, and we end up with that expression. And when we rearrange, this is our expression for the time derivative. Error is of order delta t. Okay, so now we are no longer fortuitous and have error delta t square as we had in the explicit method. It's back to delta t, which we had for the first step of the explicit method. Okay, because we are using unequal time stepping in the 2 Taylor series expansions. All right. All right, so now we plug that in. Notice that on the right hand side we have all n+1 now. No n's anymore, because it's an implicit scheme. Okay. And if we rearrange it, what do we get? Well, our well-known tridiagonal equation for 1D. Okay. So it's an implicit set of equations, simultaneous set of equations, but tridiagonal obviously. So the idea is we are trying to calculate this guy. We need 2 previous time steps, as you can see from the n-1, or sorry, here, n-1 and n in the equation. So we need both of these 2, as well as we need the neighboring nodes at the same instant of time that we are trying to calculate, which makes it implicit. All right. Now, of course, again, just like before, we cannot use this for the first time step. We can only use this for n greater than 1. Because if we plug in n equal to 1, we get, right here, we get phi 1. No, n equal to 1 will work. Sorry, this is n greater than 0 in this case. Okay. So if you plug in n equal n greater than n equal to 0, then we have problems. Okay, because we are going to hit a phi of -1, which doesn't exist. So we have to derive, just like we did for the explicit scheme, a special expression for the first time step. Okay, how do we do that? We again start with a Taylor series expansion, but now we have some additional complications because the boundary conditions are not posed. See, when we did explicit formulation, we got d phi dt at n and I here, so we could directly plug in the boundary condition for this term. Now we cannot do that. This is at n plus 1. That's not your, not boundary condition, initial condition. That's not your initial condition. Initial condition is at n. Okay. So how do we get rid of the problem? We do a Taylor series expansion of the first derivative at n about n plus 1. So this is again like a backward Taylor series expansion in time. Okay. And we now take that, we rearrange it, express this guy in terms of the d phi dt at n. Okay. And now we plug that in here. All right. So we're substituting 3 in 1, and as I said, that's where we are plugging it in. And you rearrange, simplify and rearrange. So of course this guy is now your beta I. Okay. And right here is your alpha I. The two initial conditions, one for the derivative, one for the value of phi itself. And you rearrange that, you get your second derivative, which looks like that. Okay, again, it's first order in time, as you can see, truncation error. Okay, so now you substitute it into your governing equation. For the first time step, you get this equation. Okay, of course, it again has n plus 1 on the right hand side everywhere. So that's the tridiagonal equation for the first time step. Okay. So first time step you get a tridiagonal equation, subsequent time steps you also get a tridiagonal equation, but it's a slightly different set of equations. Okay. And this is the pictorial representation. To get the value at this node, you need the neighboring nodes as well as the initial condition which shows up here. Okay, these two guys. All right, so here's the algorithm. Set up initial conditions, same as before. Step 2, you calculate all nodal values at the first time step using this implicit set of tridiagonal equations. So this is your TDMA solve. Okay. You reset initial conditions, then you go to the next time step and solve the equation for subsequent time steps, which is another TDMA solve. They are slightly different equations. Okay. And then you reset your initial condition and repeat these two steps. So the only difference is between explicit and implicit is in explicit you didn't have to solve any equations. Okay, just simple explicit formula. Here you have to solve for a 1D problem, you have to solve a tridiagonal equation. Okay, now if it's multi-dimensional, you get back to what we discussed earlier. You have to use one of your iterative solvers to solve within each time step. Okay, any questions on the algorithm? All right, so let's talk about stability. I'll just go through this quickly. These are the same steps as the explicit method, except here now you have n plus 1 instead of n. Okay, if you compare it to the explicit method. So this is our criterion for stability. We plug in our Fourier decomposition, very similar to your explicit formulation, except this xi appears here, which did not show up in the explicit method. Okay, the left-hand side here is identical in both methods. So we rearrange again using our trig identity of cosine theta minus 1 is 2 sine squared theta over 2. Simplify, rearrange, and so we get this equation now. Again, this guy we are going to call h, so that I used h because so as not to confuse with the g that we used earlier. I don't want to use g for both places. They're slightly different expressions. Okay, and of course this guy, this ratio shows up again, and that's our r, c delta t over delta x, showing up there. So 4r squared sine squared theta over 2. The two roots are that, slightly different from last time. Okay, sine squared theta equal to 1, or sorry, sine squared theta equal to 0 gives you h equal to 1, which you can see from this formula here. If I plug in 0 here, h is simply 1. All right, and if you use h equal to 1, both roots just give you 1. Okay, nothing meaningful, which basically says that it's stable. So therefore we are going to look at again sine squared theta equal to 1 instead of 0. All right. Let me see, what am I saying here? H is always greater than 1, as you can see here. Okay, so it's 1 plus some positive quantity. All right, because there's a square here, and then sine squared theta is always a positive quantity. So h is always a positive quantity, greater than 1. Okay, which means that 4 minus 4h is always negative. 4 minus 4h is what shows up here underneath the square root. That's always a negative quantity. So what does that mean? That means the two roots are always complex. Okay, so for any other value of sine squared theta over 2, the roots are always complex. Okay, for 0 it's exactly equal to 1. H is exactly equal to 1. And xi1 and xi2 are exactly equal to 1. But for any other value, they're complex roots. And for stability, the magnitude of these complex roots must be less than 1. So what I'm going to write it as, so we found that in the earlier analysis, we found that 4 minus 4h is always negative. So instead of writing it that way, what I've done is I've inverted it. I've written it as 4h minus 4 and then taken square root of minus 1 outside the square root sign. Okay, so just reversed it, reverse the sign, and wrote it that way. All right, so therefore you can now calculate the magnitude of that complex number, which is xi times xi star. Okay, the complex conjugate, xi star being the complex conjugate, which is basically the second root, as you can see. All right, and once you do some algebra here, you find that it is 1 over h square root of that. Okay, now we already found that h is always greater than 1 in the previous page. We saw that. So what does that mean? That means that magnitude is always less than 1. Okay, so since h is greater than 1, both roots will be always less than 1, and therefore the method is unconditionally stable, which is kind of an expected result, as we saw for parabolic problems. Okay, but we get the exact same result for hyperbolic problems when we do the stability analysis. Okay, so that's the conclusion we are drawing here. Let me show you an example here. So I showed you these results for the explicit method. For the same problem, if you now do implicit calculations, These are what your results look like. The errors, actually, you see, if you compare the magnitudes, now, of course, the shape of the errors are quite different, implicit versus explicit, as you can see, this plot versus that plot, okay? Quite different shapes. But if you look at the magnitudes, let's say the maximum negative magnitude is 0.01, okay? Whereas here, it's also about 0.01, but on the top here, this is about 0.01 on the positive side. This is 0.04, much larger. Okay, and the reason for that is, remember, in the explicit scheme, we found that from the second time step onwards, the scheme fortuitously becomes second order accurate. Okay, so that's why for the same time step size, for the implicit method, we are getting slightly less accurate solutions than what we are getting with the explicit method. Okay, the errors are slightly larger. The shape of the errors are also quite different, as you can see. And if you look at the solution here, on top here, we saw this kind of wiggly pattern. Oops, sorry about that. This wiggly pattern here, we don't see this wiggly pattern here. It's smooth lines which sort of get smeared out at these edges. Okay, and that has partly to do with the fact that, you know, I'm not using very large number of nodes. If I used larger number of nodes in the x direction, then I would get smoother solutions. Okay. All right. Then what happens if we go above the CFL of 1? Okay. So this is all CFL of 0.5. Both methods worked. All right. If we go above CFL of 1, this is for CFL of 2. This one I showed you already. The method blows up. Here, still bounded solution. Of course, the solution is not as good. Instead of a trapezoid, you get kind of like a parabola. Okay, but again, that has to do with the fact that I'm using large time steps, CFL equal to 2, and also I don't have, you know, super fine mesh in the x direction. Okay. But no matter what you do, the solution will always stay bounded in this case. Okay? Accuracy is, of course, a different issue. Any questions on that? So, in summary, you have, we talked about explicit and implicit methods for the hyperbolic equation. There are two challenges here. One challenge is that for the first time step, you have to do a special treatment because it has second derivative in time. So the set of equations you get for the first time step versus other time steps are different, whereas in the parabolic case, you didn't have to worry about that. Okay, that's one big issue. Second issue is that the stability criterion for the explicit method now is different from what you had for the parabolic case. Okay, there is still a stability criterion, but it's the CFL criterion now we have instead of what we had for the grid Fourier number for the parabolic equation. Okay, the implicit method, again, in parallel with the parabolic method, is also unconditionally stable in this case. All right, any questions?